Wonderful. Can you all see my screen? It has a picture of a basketball and a big round bottom flask on here that says 22.414 liters. Okay, wonderful. Excellent. Well, last class we ended here. We were talking about STP, standard temperature and pressure. Standard temperature is 273 Kelvin or 0 degrees Celsius. And standard pressure is 1 atmosphere, and that's the pressure that one would experience at sea level. And experiments have been done to show that at standard temperature and pressure, 1 mole of any ideal gas occupies, it's actually 22.414 liters, but we'll say 22.4 liters is close enough. And you have to memorize that number. Everybody in the class has to memorize this, and I'll highlight it for you, that at standard temperature and pressure, I guess it says standard temperature and pressure, 1 mole of any ideal gas. And if you're wondering how do you get that, well, the ideal gas equation, which is shown here, PV is equal to nRT. If you solve for R and you plug in atmospheric pressure and you solve for 1 mole at standard temperature and you plug in the amount of space or volume that 1 mole of a gas takes up, of an ideal gas takes up at standard temperature and pressure, you get this number here as your gas constant. So that's what R stands for. It's a gas constant, and it's 0.82057 liter atmospheres per mole Kelvin. Now, the number of significant figures that we use is going to really depend on the problem. I think the book uses, or she rounds it off a lot of times to 0.0821 liter atmospheres per mole Kelvin. But I will usually provide the gas constant for you, so you don't necessarily have to memorize the gas constant. However, you do have to memorize this number. So we're going to know that moving forward, that 1 mole of any ideal gas at standard temperature and pressure is going to take up that magical volume of 22.414 liters. Well, let's look at the gas constant in a little more detail. And this is the gas constant that we just solved for using PV is equal to nRT, and then we solved using N is equal to PV over, sorry, Mr. Dion's needs another drink of coffee, I guess, so is equal to PV divided by NT, like that. Okay, well, now where we would use this gas constant, 0.0821 liter atmospheres per mole Kelvin, we would use that in gas laws problems, right? And what's the subject of chapter 5 is we're dealing with gases, right? So we're going to use that most of the time in this chapter. However, if we're ever doing mathematical equations that involve energy and we want to determine energy in joules, well, what gas constant will we use then? Well, we're actually going to use this value shown right here below, 8.31 joules per mole Kelvin. And if you're wondering, well, how did you get a different number for the same thing? Well, it's just expressed using different units, right? Keep in mind, these are all values of the gas constant, just expressed with different units. And if you're wondering, you know, how did we get from here to here? Well, the way that using 100 times atmospheres, that's kind of an interesting or strange way of expressing energy, but it is an energy term. So that's if we are using equations that involve energy in joules. And then finally, later on, and this will probably be during the next lecture, we're going to talk about the speed of molecules or atoms. And when we are determining molecular speed, we're going to use this value for the gas constant down here, 8.31 times 10 to the 3. So times 1,000 grams times meter squared divided by second squared times mole times Kelvin. If you're like, wow, that one's really weird. Well, keep in mind, if any of you have studied physics, you've seen this conversion factor before, which is that 1 joule is equal to 1,000 grams meter squared per second squared. And what you might even be more familiar with is 1 joule is equal to 1 kilogram meter squared per second squared. So again, different values for R, and it's just going to be depending on what kind of mathematical problem we're tackling. Nothing more than that. So other values for the gas constant. You know what? And if you Google the gas constant and look up other values, you could probably go on something like even Wikipedia and look up different values for the gas constant for different different scenarios, I should say. Anyhow, before we start doing some problems, let's talk about some example conversions here. It says at room temperature, we have some dry ice, which is nothing more than solid carbon dioxide. So if you ever see this written anywhere in chemistry class, if you ever see CO2, it's usually written as a gas like that. And that's carbon dioxide gas. But if you see CO2 written with an S beside it, that means that you're talking about dry ice. And I'm sure somebody who's hearing the sound of my voice has played with dry ice at some point in their life. Got to be careful. Anyhow, at room temperature, dry ice sublimes. It goes directly from the solid phase to the gas phase, so it becomes a gas. At 77 degrees Fahrenheit, 13.6 ounces of dry ice are put into a steel tank with a volume of 10 feet cubed, or 10 cubic feet. The tank's pressure gauge registers to 11.2 psi. Express the volume of the tank in liters, the amount of CO2 in grams and moles, and the temperature in degrees Celsius and Kelvin, and the pressure in bars, millimeters mercury, and atmospheres. Look, most of these conversion factors, or most of these conversions, are things that we've already looked at in this class. So I'm not going to spend a lot of time, doing every conversion under the sun. Okay. By now, we've already looked at this. I remember looking at this with you just the other day. We said that when Evangelista Torricelli did his experiment at sea level, the inverted column of mercury at sea level, again, measured at a height of 760 millimeters of mercury, and that's at 1 atmosphere, or sea level. So we've already looked at that. We already know how to convert numbers of moles into grams and things like that. Okay, there's some other conversion factors here that you might not be as familiar with, but you should be able to do any kind of conversion given a conversion factor. Now let's just move on to the next slide. And I'm not going to walk through all these right now, but I have them all worked out over here. So we have the volume in cubic feet. That's what was given to us in the problem. And we know that there are 28.32 liters in 1 cubic feet, 1 cubic foot, I should say. Yikes. So we end up with 283.2 liters. It's asking us to express the mass of the carbon dioxide in grams, but they've given us ounces, and we know that in 1 gram there are 0.03527 ounces, so we just use that conversion factor. So now we have the volume of the steel vessel, we have the mass of the carbon dioxide. Hey, now that we've got the mass, you guys should be able to convert the mass of carbon dioxide into the number of moles of carbon dioxide in your sleep. You've done it so many times by now, right? You know that the molar mass of carbon dioxide is 44 grams in 1 mole. Grams and grams cancel out. We're left over with 8.77 moles. Temperature conversions, we looked at those at the very beginning of the class. I told you that you have to know how to convert from degrees Fahrenheit into Celsius, or Celsius into Fahrenheit, one or the other, and then you can always rearrange that equation. So to convert from Fahrenheit into Celsius, we simply subtract 32, divide by 1.8. We get our temperature in Celsius is 25. We add 273 to that to get our temperature in Kelvin, right? And then for the pressure conversions, we're going to convert to atmospheres from PSI. We've been given that conversion factor, so we have the pressure in atmospheres. If you want that into millimeters of mercury, I'm missing the HG here. I'll fix that for you. Anyhow, so atmospheres cancel out. And then if we wanted to do bars, well, if we have this conversion factor that there's 1.013 bars in an atmosphere, well, again, you can see the atmospheres cancel out, and we'd end up with our pressure in bars. Okay, so again, you should be pretty solid at your conversion factors by now, right? And if you think about, the gas laws that we've looked at, Boyle's law, Charles' law, Avogadro's law, and then we looked at the ideal gas law. Well, thinking about those calculations that we looked at, I'm going to skip that problem and go right ahead to this slide here. We've kind of got 2 scenarios that we've looked at so far, and that's the first 2 bullet points here, the final state of a gas and the single state problems. So the final state of a gas type problems, those are the kind of things where we calculate from its initial and final state, right? And we get the changes in pressure, volume, number of moles, or temperature. And when we solve those kinds of problems, what we're talking about are things like Boyle's law. So Boyle's law, Charles' law, Gay-Lussac's law, Sachs law, combined gas law, Avogadro's law. I'll just put those on the Avogadro's law, right? Those are things where we did, P1 and P2 and V1 and V2 and N1 and N2, so on and so forth. But single state problems, those are where we are going to determine either one of these four variables: pressure, volume, number of moles, or temperature, given the other three. And what equation did we use to do that? Well, I think everybody could answer that one, with very little thought too. And that's the ideal gas equation, right? PV is equal to nRT. Well, what we're going to look at today, we're going to look at density problems. And we're going to be able to determine the density of a gas by having its molar mass, or we can determine the molar mass of an ideal gas with only having its density. Okay, and what you're going to see is that we're going to solve the ideal gas equation, and we're going to determine that density is equal to pressure times molar mass, that's what the double MM stands for, over RT. And if you're wondering, where would I get that equation? Are you going to give me that equation? The answer is no. I won't give you that equation, but I'm going to show you and give you the tools that you need to derive that equation, okay, so that you won't struggle when it comes time to solve any problems that deal with density, okay? So again, we haven't looked at that yet, but we're going to try and look at it today. Well, let's go back to that first bullet point, right? The Boyle's laws, the Charles laws, Avogadro, so on and so forth, right? And this isn't if, this is initial and final version of gas laws, right? Things where we were looking at the initial state of a gas and the final state of a gas. In this type of problem, a gas undergoes some kind of change from its initial to final state. The ideal gas equation is basically written twice, once for the initial state and once for the final state, and then we're going to cancel anything that doesn't change, right? And that is essentially how we end up with those laws: combined gas law, Boyle's law, Charles' law, and Avogadro's law. So technically, you can derive Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law from the ideal gas equation. So as long as you have PV is equal to nRT memorized, it can get you out of a bind, even though we do expect you to memorize, Boyle and Charles and all those things. Well, with that in mind, let's take a look at a problem. Sample problem 5.1 says a sample of air is originally at 32 degrees Celsius. If pressure and number of moles are kept constant, to what temperature must the air be cooled to decrease its volume by 25%? Let's think about this in terms of the ideal gas law just for a second, okay? Because I just want to prove to you that if we write PV is equal to nRT, well, what's it telling us in the problem? They're telling us that pressure is staying constant and number of moles is staying constant. The gas constant is a constant, so we're dealing with volume and temperature. And what do you see here? You see that volume is directly proportional to temperature. And therefore, we can write V1 over T1 is equal to V2 over T2, which is Charles' law, right? So this is nothing more than Charles' law, all right? Now we can plug in some numbers. Now, we've been given the initial temperature. They always have to give it to us in degrees Celsius, and we have to convert that into Kelvin. So we're going to take 32, and we're going to add 273, so 32 plus 273, and that gives us 305 Kelvin. So our T1 is equal to 305 Kelvin. We're looking for what temperature? So we're looking for our T2. So put T2 is equal to something. And then it doesn't give us a specific volume. It doesn't tell us, well, the volume is, 10 liters or something or anything like that. It just tells us that it decreases by 25%. Now, there are literally Avogadro's number or an infinite number of numbers that you could plug in to the formula. But I'm just going to use something really simple. Let's say that my initial volume is 4 liters. If my volume decreases by 25%, right? If I have 4 liters and I decrease that by 25%, can anybody answer how much would I have left over? How many liters would I be left with? What would my V2 be equal to? Decrease by, exactly. Thanks, Jamil. Exactly. I see everybody just typing in 3, and you're all 100% correct, right? So we're going to have our final volume as being 3 liters, right? And I'm going to put this in here. Remember, we're decrease by 25%. And remember, don't think that you have to plug in 4 liters and 3 liters. You know, you could plug in 10 liters and 7.5 liters, right? Which is also a decrease in 25% of 10 liters. That will give you the exact same answer. Don't believe me? Try it out, okay? But I promise you that if you plug in any number for a volume and then decrease that by 25% or multiply it by 0.75 and use that as your final volume, it's going to work. You're going to get the same T2. Well, let's take this formula, Charles' law, and let's solve it for T2. And we get that T2 is equal to V2 times T1 divided by T1. Nope, divided by V1. Good gravy, Mr. Dion. There we go. All right. Now we're just going to plug in some numbers. We have our 3 liters. We have our initial temperature, which is 305 Kelvin. And then we're dividing that by our initial volume, which was 4 liters, like that. I'm going to double check my math. I did do this one ahead of time. So we get 915 divided by 4. Gives you 229. Is that what I put? Yeah. Anyhow, I put in way too many sig figs. You can assume that these have an infinite number of sig figs. But anyhow, I'll report it to 3 sig figs. So it's 229 Kelvin. And then if we want to convert that into degrees Celsius, so this is the final answer. T2 is 229 Kelvin. If we take that, since we know that temperature in degrees Celsius is equal to temperature in Kelvin, subtract 273, okay? We're going to take 229 and we'll subtract 273. I'm thinking too much here, and we get minus 44 degrees Celsius, okay? So either one is an acceptable answer, but as you know, if you've written any exams, which you all have in Chemistry 1401, you know that in multiple choice questions, we love to mix up units, you know, we'll make you solve it in Kelvin and give you the answers in degrees Celsius, but that's just a way to ask our students more than one thing in the same question, you know, just to be sure they're on their toes. Let's look at a single state problem. And we looked at a couple of these last class, but hey, practice makes perfect. Calculating pressure, volume, number of moles, or temperature using the ideal gas equation. And in case I haven't, you know, explicitly said it, you have to memorize this equation. So memorize. You're never going to walk into any kind of exam on chemistry. I don't care if it's the MCAT or a DAT or a PCAT or, you know, a HASI exam, anything. They're always going to expect that you have pressure times volume is equal to nRT. Okay, they're always going to expect you to have that memorized. Now, in this type of problem, we're going to have, you know, say pressure, volume, number of moles, and we'll have to solve for temperature, right? So we're always left with one variable that we don't know, but we can always manipulate the ideal gas equation to solve for that. Now, this is just, you know, Mr. Dion being a dad here, but it says take care to follow the units. Okay, I can't stress that enough. I know a lot of my students are really crackerjacks at any kind of problem with ideal gas laws, and I think that's wonderful. I love it when the students are very proficient and they're confident in their abilities, but don't get so confident that you just start scribbling numbers on a piece of scratch paper and don't have any units, okay? If you put the units in, then you can always double check it. You probably notice that every time I solve a problem, or at least I try, every time that I do a problem to show my units and show my students everything's working out, because, you know, I've seen students make that little mistake where they have the wrong unit and, you know, even though they were confident, and they might get the wrong answer. Anyhow, that's enough of me lecturing you about that. Let's take a look at a problem. Here's the ball and stick model of sulfur hexafluoride. Who could tell me, this is just a little quiz for my students who are with me today on this snowy day. Who could tell me what the molecular geometry of sulfur hexafluoride is, this beautiful molecule right here? Who's got a molecular geometry on the tip of their tongue or at their fingertips? Yeah, absolutely, Aaron. Yes, this is octahedral, right? Octahedral. All the bond angles are all 90 degrees. You know. Here we go. Anyhow, so sulfur hexafluoride is a gas used as a long-term plug for a retinal hole to repair detached retinas in the eye. If 2.5 grams of this compound are introduced into an evacuated 500 milliliter container at 83 degrees Celsius, what pressure in atmosphere is developed? I mean, look, you can see here that we have mass, right? We have the mass, But can we calculate number of moles from mass? Absolutely we can. In fact, I've even gone ahead and looked up the molar mass of sulfur hexafluoride, which is 146.06 grams per mole. Right? So if we have the mass in grams, that means that we can calculate N. We have the volume of the container, and we also have the temperature. It's not in Kelvin, but we've got it. So if we look at PV is equal to nRT, what have we got? We've got N, we've got T, we got V, and we have the gas constant. Can we solve for P? The answer is absolutely we can, right? We can solve for P. We know that P is going to be equal to, son of a gun, I got R on the brain here, don't I? We got P is equal to nRT over V, just like that. Well, let's solve this problem where we have a little more space set aside here. Let's do some math. We're starting it with 2.50 grams of SF6, and as I told you, 1 mole of SF6 has 146.06 grams of SF6, and we cancel out our grams, and we end up with our number of moles, which I have written down here, is 0.0178. 0.0178 moles of sulfur hexafluoride. Okay, we got that. What else? We have our volume, right? So this is equal to our N. Our volume is equal to 500.0 milliliters, but we know that in 1 liter we have 1,000 milliliters, and so we'll do some math here. Make sure our units cancel, and we get that our volume is equal to 0. Get a little overzealous here, 0.5000 liters. So again, that's equal to our volume. What else do we have here? We have our temperature. Temperature is equal to 83 degrees Celsius. All we have to do is add, let me just do it like this. We'll say plus 273, and that gives us the temperature in Kelvin. Did I calculate that? 356, so 356 Kelvin. Let me double check that. 356, and there we have it. So now we can take our ideal gas equation, PV is equal to nRT, and we can solve for P. P is equal to nRT over V. Let's plug in some numbers. We've got our number of moles, 0.0178 moles. We've got our gas constant. I got that memorized, 0.0821. I don't need more than 3 sig figs, so I'll just use 3 liter atmospheres over mole Kelvin, like that. Put in our temperature, which was 356 Kelvin, and we'll divide all that by our volume in liters, which is 0.5000 liters. Let's do that double check of those units. Liters cancel, moles cancel, and Kelvins cancel. What am I left over with? Atmospheres, which is a unit of pressure. And so when I punch all that spinach into my calculator, Mr. Dion likes his spinach, doesn't he? We get our pressure is equal to 10.7 atmospheres, just like that. Okay, I can guarantee you 100%, give you my money back, Mr. Dion's money back guarantee, that you're going to see some kind of problem on the next exam that involves the ideal gas equation. Guaranteed that you're going to have to apply this gas equation, ideal gas equation, probably more than once. And so again, you see how by having N, P, and T, and of course the gas constant R, we're able to solve for our pressure. Okay, give me a thumbs up if you follow me on that problem. It's not meant to be a mind boggler or anything. Just supposed to be fun, right? Supposed to be fun, nothing more than that. Well, let's switch gears and get into that density thing that I promised, right? I promised you that we were going to talk about the densities of gas. You remember that the other day I told you, and I don't expect you to remember everything I say, right after I lecture on it, but do you remember I told you that when we're looking at the densities of gases, we measure them in grams per liter, right? We take a much bigger volume since the densities of gases are so low. But you know that density is equal to mass over volume, don't you, right? Everybody who's hearing the sound of my voice knows that density is equal to mass over volume. Let me show you another equation that you all know too. N is equal to M, little m, over double big M, like that. And if you're wondering, what the heck is that equation? N is number of moles, right? Number of moles is going to be equal to mass in grams divided by molar mass in grams per mole, right? And now you're probably thinking, yeah, I get it, right? Grams cancel out. Well, we can use these two equations. Density is equal to mass over volume, and N, which is number of moles, is equal to mass over molar mass. And we can solve the ideal gas equation to determine the density of a gas. Let me show you how to do it. Now, there's not a lot of room on here, but I want to do it on this slide to kind of walk you through it here. So if we write down, let me use the red pen, okay? If we write down PV is equal to nRT, we can plug this M over double big M, mass over molar mass, in the place of N. Watch. Now we're going to rewrite it like this. We're going to say pressure times volume is equal to mass over molar mass times RT. Look, all I did was express the number of moles as mass over molar mass. So nothing really that crazy so far. Well, hold on. If I know that density is equal to mass over volume, hey, look, I've got mass and I've got volume. I could rearrange this equation and solve for density, couldn't I? Yeah. You can say density, which is equal to mass over volume. We solve for mass over volume. What do we get? We get pressure times molar mass divided by RT. That's equal to our density. Pretty cool, huh? Give me a thumbs up if you think that's kind of neat. We solve for the density of the density of a gas with nothing then other than its pressure and its temperature and the molar mass of that gas. Yeah. So you will be expected to be able to derive this equation. Okay. Let's write that down as a note. Okay. We'll put it here. Must be able to derive, or there is another option if you're like, I don't want to derive that. Okay. Or you can memorize it. Okay. Because we will not provide that equation. Memorize. Okay. Those are your two options. I'll be honest with you guys. I've taught this class enough to know that historically with my students, I'd say it's probably a 50-50 split. Okay. Probably half of my students like to derive it and half of my students memorize it. And I say, huzzah to both of them. Okay. All I care about is that you're able to, get the right answer on the problems in class. Okay. So here it is, just kind of written out a little bit bigger, right? And there's sort of one small detail missing from this. And the reason I left it out is because I know that my students know that N, number of moles, is equal to mass over molar mass, right? Mass in grams divided by molar mass in grams per mole, like that. Okay, and that shows that not only do we have this equation that we just derived, density is equal to pressure times molar mass divided by RT. Hey, if we have density of a gas, hey, what do you know? We could solve for the molar mass, couldn't we? Absolutely, we could. Well, I want to take this equation, D is equal to pressure times molar mass divided by RT. I'm going to copy this equation. Copy. And I'm going to take it with us to the next slide. Okay. And I'm going to paste it here. Okay. This equation wants to keep this in mind. So density is an intensive property. It doesn't depend on the amount of the substance, right? The density of water is approximately 1.00 grams per centimeter cubed or 1.00 grams per milliliter. Doesn't matter if you have, a bathtub full of water, if you have a swimming pool full of water, if you have a lake full of water, if you have a thimble full of water, the density doesn't change, right? That's intensive. But the density of a gas does depend on what? Look, if you look at this equation, you can see that the density depends on pressure, depends on molar mass, and it depends on temperature. Okay, so the density of the gas depends on all three of these variables. So let's look at a figure that demonstrates this. Now I'm going to see, does the paste feature work from slide to slide? Mr. Deanna's nuts. What if I do this? Paste. Hey, it worked. Okay, here we go. I wanted to bring this equation with us for another sort of demonstration, if you will. Let me move this out of the way a little bit here. I love the title of this slide. So descriptive. Balloons. So here you have some balloons. In the first picture, it says The yellow balloon contains helium, right? So there's helium gas in here. Helium has a molar mass of what? It's around, I don't know, what is it, 4.04? Yeah, 4.0, we'll just put 4 grams per mole, okay? That's the molar mass of helium. Whereas the other balloons are filled with air. Now, air, the average molar mass of air is around 30 grams per mole. It's probably less. It might be 29 or something, but close enough for jazz, okay? Now, if we look at our equation, density is directly proportional to molar mass. That means the lighter, right, the gas, in terms of its molar mass, the lower density it's going to have. And that's why helium floats in air, right? You can imagine that hydrogen is also going to float in air, right? It's got an even lower molar mass, okay? So from this equation that you are going to be able to derive, okay, or you might even already be able to do it, you can see that density and molar mass are directly proportional. Let me show you another example. Okay, same equation. Density is equal to pressure times molar mass divided by RT. And let's look at part B here, the second picture. It says, oh, it even says here, damn it, this would be on, you gotta read it more carefully. The higher molar mass, ooh, there's this mistake slide. Anybody notice this? Molar mass, 29 grams per liter. That's not right. It's grams per mole. All right. Anyhow, there we go. Where was I? I was in the second picture. Look, these are just some hot air balloons, and you see that a couple of them are up in the air. You know, I can't tell if this one here is maybe on the ground. I don't know. Anyhow, you see you have a grounded balloon, and then you have some that are in the air. Well, what's the difference? Is one of them filled with helium? No, of course not. Nobody has that much helium to fill up a balloon. That's crazy. Okay? What's the difference? The reason they call them hot air balloons is because when you take that air, right, the molar mass of the air isn't changing, right? I told you the air was 30 grams per mole here, and the book argues with me, it says it's around 29. Well, whatever the hell, doesn't matter. The molar mass of the air doesn't change, right? The air is always going to be around 29 grams per mole. Okay, if you're a stickler, I'll even change this one here. I'll delete that and we'll put in 29 grams per mole. Okay, good enough. But what do we know? We know that density is inversely proportional to temperature. So that means as temperature goes up, density is going to go down. So as the balloons get hotter, the density of the air inside gets less and less and less. And that's why a hot air balloon floats. Right? The same rationale applies on the other side. Right? As molar mass goes down, density also goes down, right? Because they're directly proportional. We can put it here, density directly proportional to molar mass. I'll put here, density inversely proportional to temperature. This slide is really nothing more than qualitative analysis of this equation. But give me a thumbs up if you follow me, or let me know if you have any questions. All right, great. It's always nice to see that my students are on the same page as me, right? Or the same slide as me. Anyhow, so now we're going to kind of switch it up a little bit, okay? We're going to kind of take two concepts that we've looked at in detail in this class, and we're going to wed them, right? We're going to bring them together. So now we're going to be talking about gases, ideal gases. We're going to be using the ideal gas equation, but we're going to look at it in terms of stoichiometry. Okay, we spent quite a bit of time talking about stoichiometry, right? Balanced equations, number of moles of a reactant using a balanced equation and a conversion factor derived from a balanced equation to determine the number of moles of a product, let's say. Okay, so gases can participate as reactants or products in any chemical reaction. Gases are balanced in the same way as liquids, solids, or aqueous solutions. Right? By now you know how to balance an equation. But there's a big difference when we're dealing with gaseous reactions, or gases in reactions. Sorry, gaseous reactions, I should say. Balanced equations can be used to relate moles or grams of substances, and in gases, we can also include volumes. And the reason we can do that is because of Avogadro's law. Right? Remember this. We looked at a figure almost identical to this in quite a while ago. I'm talking like a month or two ago. You know, when we talked about the amount of something in grams, a reactant, And if we want to use that to determine the amount of a product in grams, we would have to proceed through moles, right? And then we would use, in here, we'd use balanced equation, right? In order to get us from moles of reactant to moles of product, or vice versa, it doesn't matter. But what's different about gases is that we can also use volume, okay, or volumes, and we can go directly from volume to volume, right? Why? Because of Avogadro's law, okay? Well, with that in mind, let's take a look at an example, and it should become, should crystallize once you see the concept in action. Hydrogen peroxide is a common bleaching agent. It decomposes quickly in water and oxygen gas. It should say it decomposes quickly to water and oxygen gas. Let me just fix the grammar here. The way I read it would be like that. Hydrogen peroxide is a common bleaching agent. It decomposes quickly to water and oxygen gas at high temperature. So here's the balanced equation. How many liters of oxygen are produced at 78 degrees Celsius and 0.934 atmospheres when 1.27 liters of hydrogen peroxide, and they give us the density, decomposes? Well, let's take a look at what we're given here. We're given a beautiful balanced equation, and we know that we're starting out with 1.27 liters of hydrogen peroxide, okay? And what we're trying to determine is we want to figure out the volume of oxygen, right? How much oxygen is produced? Well, what I would say is this. If we solve for the volume of oxygen using the ideal gas equation, right? PV is equal to nRT. We can rearrange that to solve for volume, and that's equal to nRT over P, like that. We've got the pressure, right? That's been given to us. We got the temperature, also given to us. We got the gas constant. So what do we really need here in this, problem? What are we actually solving for first? The first thing we need to solve for is the number of moles of oxygen, right? That's what stoichiometry was about. Remember, we aren't given a gas, right? We're starting with a liquid, so we can't convert from liters to liters using our balanced equation. We're going to have to go from grams to number of moles, and then we can determine the number of liters. All right. Well, let's start doing some dimensional analysis. I've been given the volume of my H2O2. I'll write it down here again, 1.27 liters of hydrogen peroxide. And I know my density is that in 1 gram, in 1 milliliter, I have 1 gram of my hydrogen peroxide. Let's convert that liters into milliliters first. And we know that in 1 liter, we have 1,000 milliliters. And then we know that we have 1.00 grams in 1 milliliter. Look at that. My liters cancel, my milliliters cancel, and I'm left over with grams of hydrogen peroxide. Now, did I solve that? No, I didn't. I actually went one further, and I solved for the number of moles of hydrogen peroxide. So let's do that. And to do that, I need the molar mass of H2O2, which I already looked up as being 34.01. Yeah, 34.01 grams per mole. So I can use that conversion factor. Then in 34.01 grams of H2O2, I have 1 mole of H2O2. So let's put all that spinach together. And you see that grams cancel, H2O2 cancels, and I'm left over with moles of H2O2. So again, I solved for the number of moles of H2O2, or the number of moles of hydrogen peroxide, and I got 37.3 moles of H2O2. So now, instead of writing down, 1.27 liters, I can erase that and say, hey, I'm actually starting out with 37.3 moles of H2O2. Now, how am I going to take that and solve for the number of moles of oxygen? Well, look, I have a balanced equation, and I know that if I have 37.3 moles of H2O2 reacting from my balanced equation, I know that for every mole of hydrogen peroxide that gets consumed or decomposes, I'm going to produce, sorry, I know that for every 2 moles, I didn't look at my balanced equation closely enough, for every 2 moles of hydrogen peroxide that decomposes, I produce 1 mole of oxygen, like that. Okay, now I could have added, or I could have tacked this conversion factor on, just kept going. I'm kind of breaking it up stepwise. Sometimes I do, sometimes I don't, depends on the problem. Anyhow, we end up with a total of 18.7 moles of oxygen. Okay, now I'm going to take this. I'm going to copy that. Copy. And I've made another slide here just so I have more space. So we're going to plug that in, paste, and now we have our number of moles of oxygen. Again, we have our ideal gas equation. PV is equal to N nRT. We want to solve for the volume of oxygen, so it's going to be equal to nRT divided by P. Well, let's solve the temperature for Kelvin. So we take 78 and then we add 273 and we end up with 351 Kelvin. We have our pressure in atmospheres. So now we got our temperature, we got our pressure, we got our number of moles. I mean, we don't need anything else. It's all there, right, people? We got 18.7 moles of our oxygen multiplied by our gas constant, 0.0821 liter atmospheres per mole Kelvin. I don't need more than 3 sig figs. What's next? My temperature? Yeah, 351 Kelvin. Go. I'm going to divide all that by my pressure, 0.934 atmospheres. And let's check our units. Atmospheres cancel, moles cancel, and Kelvins cancel. Hey, I'm left over with the units of liters, which are volume. And so the volume of my oxygen that's produced from the decomposition of that 1.27 liters of hydrogen peroxide is 577 liters. Okay. There we go, 577 liters. Holy schlamolts. Is that a lot of volume for, 1.27 liters? That's crazy. 577 liters. I mean, think there's what, 3.94 liters in a gallon? So if we take that, and I'm just kind of doing a back of a napkin here. So I mean, that's almost 150 gallons of gas that you generate from what? 1.27 liters. That's what, a third of a gallon. You take a third of a gallon of a liquid and you end up with almost 150 gallons of gas. Now do you understand that gases are mostly empty space, right? The particles are much farther. Yeah, somebody says that's insane. It's true. And if you think about it, something like airbags. So airbags involve the decomposition of sodium azide, and you end up, I won't write the whole balanced equation, but you end up producing nitrogen gas. And so you start with sodium azide, which is a solid, and you end up with nitrogen gas, and you end up with this huge volume of nitrogen gas in the airbag compared to this little tiny bit of solid that's stored inside the steering wheel. Anyhow, and that, kind of ties into the kinetic molecular theory of gases that we're going to look at even more, in an even greater detail is what I should say, later on in this class. All right, let's try another problem here, and this one's a real doozy. And I don't mean that it's difficult. I just mean it's just, it's kind of long the way it's worded here. It says aqueous lithium hydroxide solution is used to purify air in spacecraft and submarines, and that's true. It's still used to this day to purify air in a submarine or a space shuttle or whatever, space station, I don't know. All right. Because it absorbs CO2, which is an end product of metabolism, and that's according to this equation. So you take some lithium hydroxide, you have an aqueous solution of it, and it starts to react or absorb, if you will, the carbon dioxide from the atmosphere, and then you produce just lithium carbonate, which isn't harmful, in water. So you end up removing that, carbon dioxide from the atmosphere in that, closed vessel where humans, humans are kept inside of it. I don't know, struggling for words here. Anyhow, the pressure of CO2 inside the cabin of a submarine, having a volume of 2.4 times 10 to the 5 liters, that's a big space, comparatively speaking, right, compared to, I don't know, a closet, I guess, is 7.9 times 10 to the negative 3 atmospheres at 312 Kelvin. A solution of lithium hydroxide of negligible volume is introduced into the cabin, and then the pressure drops. The pressure of the carbon dioxide drops to 1.2 times 10 to the negative 4 atmospheres. How many grams of lithium carbonate are formed in this process? So what we're looking for is we want to determine the mass of lithium carbonate. But as you can imagine, before we can do that, we need to determine what? We need to know the number of moles of lithium carbonate, right? That's what we really need. And what are we given to solve that? Well, we get a balanced equation. And the only information that we're really given, besides the volume and the temperature of the submarine, or the atmosphere inside the submarine, are pressures, right? We're given an initial pressure, right? We're given a pressure initial of what? 7.9 times 10 to the minus 3 atmospheres. And then we're given a final pressure, which is 1.2 times 10 to the minus 4 atmospheres. So we get an initial pressure and a final pressure. You can also see that the ratio, the stoichiometric ratio of carbon dioxide to lithium carbonate, rather, is 1:1. Okay, so that actually kind of makes it a little bit easier, right? It's a 1:1 ratio. All right, well, with all of that in mind, why don't we find the number of moles of carbon dioxide, right? Because if we have the number of moles of CO2, from that balanced equation, we can determine the number of moles of lithium carbonate. Now I'm going to move over to the next slide, and we're going to talk about this even more. We've got a little more space, and we're going to talk about the ideal gas equation. Because if I want to measure the amount of CO2, right, we know PV is equal to nRT. If I want to figure out the number of moles of CO2, it's going to be equal to pressure times volume over RT. Well, let's think about this, because it's going to be equal to the initial pressure of my carbon dioxide, right? PCO2I times volume over RT, right? And then I'm going to subtract my final pressure of my CO2 times volume over RT. What do you notice is the same in both of these? Volume over RT. So we can, in fact, factor that out. And when we do, we get this. We get the pressure of the carbon dioxide that we start with, subtract the pressure of the carbon dioxide that we end up with, multiplied by, maybe I could do a little meter here, couldn't I? Multiplied by, good gravy. Let me move this up a little bit. There we go. Let me see if I can find more things to complain about, right? Let's see here, volume over RT, like that. Okay, so when I want to calculate my number of moles of carbon dioxide, it's going to be equal to, what did I start with? 7.9 times 10 to the negative 3 ATMs, subtract 1.2 times 10 to the negative 4 ATM, multiplied by, I have this written down here somewhere, 2.4 times 10 to the 5 liters, divided by my R, which is 0.0. Oh, I'm just looking at my notes here. Mr. Dion even got so lazy that he didn't even write the units in for R. I just wrote the letter R. That's not good practice, is it? Multiplied by our temperature. What's our temperature? Hey, they gave it to us in Kelvin. It's our lucky day, right? Anyhow, so we have all that. Let's see if our units work out. Got a different color here. We got atmospheres. Let's cancel out. We got liters. That cancels. And we get Kelvin, and we end up with moles in the denominator of the denominator, which makes it a numerator. So when you punch all that spinach into your calculator, NCO2 ends up being what? You think I'd have it written down? Yeah, it equals 73. So 2 sig figs, 73 moles. Now, we know that if we have 73 moles of CO2, we know that for every 1 mole of CO2 that gets consumed, we produce 1 mole of lithium carbonate, Li2CO3. And I've gone ahead and calculated the molar mass of lithium carbonate. And in 1 mole of lithium carbonate, I end up with 73.891 grams of lithium carbonate. Comme ça, as we say in French. Moles of carbon dioxide cancel, moles of lithium carbonate cancel. We're left over with a mass of lithium carbonate, which is equal to 5.4 times 10 to the power of 3 grams of lithium carbonate. Okay, and what does that mean? Oh, sorry. So da, 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 5.4 times 10 to the 3 grams, or I don't know. You could express it. You could just say 5.4 kilograms. If you don't need 2 sig figs. By the way, give me a thumbs up if you follow me on that one. Kind of an interesting problem, isn't it? All I see is Amanda's last comment. Okay, thanks, Blake. Aaron, good. Alexis, gang, excellent, excellent. All right, let's move on and talk about a new concept, which is Dalton's law of partial pressures. Dalton's law of partial pressures, which is nothing more than this. When volume and temperature are held constant, excuse me, it says it right here. When volume and temperature are held constant, the total pressure of a mixture of gases is equal to the sum of the pressure of each individual gas if it was on its own. So picture's worth 1,000 words, right? If you had a gas, okay, that has some kind of pressure, and you have a second gas that has another pressure, you can see the second gas has more pressure. When you put those two gases together, to determine the total pressure, all you do is add them up. And so Dalton's law of partial pressures can be expressed like this. P total is equal to P1 plus P2 plus P3 plus P4, so on and so forth, like that. And if you're thinking, hey, that's the easiest, equation I've learned in this class, hey, that's great. Yeah, you just add all the pressures of the gases of each individual gas together. Now let me show you something kind of interesting here. Collecting a gas over water. This is one of those scenarios where the whole thing doesn't fit on here, okay? So this is the title of the slide is called Collecting a Gas Over Water. I'll scroll up here a little bit. And this is an example of where you might want to produce a gas. Now, they don't have any gas being produced here, do they? Oh, yeah, they do. I guess I do down here. Let's say you needed a small amount of a gas, and I mean a really small amount. You wanted to have some oxygen gas. Well, there's a couple of ways you can get oxygen gas. The first one is you buy it, okay? You can buy it in a tiny little tank. Kind of looks like a little small scuba tank almost. Looks like this, right? And then you have a regulator that you put on the top, and you can measure with a dial or whatever, and you measure the gas. It's got a valve on it or whatever. Okay, that's called a lecture bottle, and I'm not kidding. That's what it's called, a lecture, like a lecture that you're in right now. A lecture bottle. That's one way to get a gas, so you could buy it, but those are expensive. If you needed just a small amount of oxygen gas, say, here's what you could do. You could take potassium chlorate, so that's KClO3. You could take some potassium chlorate, put it in a sealed test tube with a piece of hose coming out of it, like this, okay? So see if you can follow me here. I'll kind of walk you through this diagram step by step. So you take your KClO3 solid in here, and you start heating that up with a Bunsen burner, okay? And what that's going to do is that's going to decompose into potassium chloride, which is a solid. Not interested in that. But it also decomposes into oxygen gas, and that's what you want to collect, is the gas. Well, you're wondering, well, how do I collect the gas? That doesn't sound easy. Well, here's what you do. Take a test tube, or I don't know what this is supposed to be. I would have drawn a graduated cylinder, but whatever. I'm not the author of the book. You take some kind of tube, okay, like this, and you fill it up to the brim with water, okay? So you fill this stinker completely with water all the way to the top, and then you're going to put some kind of, piece of plastic or something over the top so that it's completely filled with water, and then you're going to invert it into a big beaker or a tray or something filled with water so that the tube is inverted and it's completely filled with water. Give me a thumbs up if you follow me thus far. Okay, so far we have an inverted tube. It's not drawn in the diagram, so that's why I'm asking if you follow me. We have an inverted tube in the water, completely filled with water. Okay, good. All right, so what you do is you heat up the potassium chlorate, right? You start making oxygen gas. That's going to go through this tube, and then you place that tube inside that inverted bigger tube filled with water. And as the oxygen gas bubbles up, what's it going to do? It's going to start displacing the water, right, and pushing it out. And you're going to start collecting oxygen gas in here. Now, you know that water has a vapor pressure associated with it. How do I know that water has a vapor pressure? If you pour a glass of water right now and put your face over top of it, you don't feel a rush of water vapor against your face, right? No. But if you leave a glass of water out, let's say overnight or for a couple of days, and you come back, you know that the volume of water in the glass or cup, whatever, it's going to decrease. Not by a lot, but it's going to decrease. Why? Because some of the molecules of water at the surface of the water have enough kinetic energy that allows them to escape from the liquid phase into the gas phase. And so we know that the water that's at the surface here on this test tube, or whatever it is, okay, that not only do you have inside here, not only do you have the pressure of the oxygen gas, PO2, you've also got the pressure of the water that's pushing up there too, right? Because this is water, okay? So based off of Dalton's laws of partial pressure, which is P total is equal to P1 plus P2 plus P3, so on and so forth, what's the total pressure inside here? It's the pressure of the oxygen gas plus the pressure of the water vapor, okay? It's being shown here. P total is equal to the pressure of the gas plus the pressure of the water. So if you want to figure out what the pressure of the oxygen is, right, you would just rearrange this equation. You'd say the pressure of the oxygen is equal to the total pressure, subtract the pressure of the H2O. Now you're thinking, like, well, how do I get the pressure of the water? I don't know. The way you would get the pressure of the water is you would look at a table. And I just happen to have that table, beautiful table, in your slides right here. Shows a pressure versus temperature curve for water. And you can see that around, I don't know, 25 degrees Celsius. Oh, good gravy. I'll try my best. I'm not a pro at drawing straight lines, but let's say you're at, I don't know, maybe I could do it at 20 degrees Celsius better. But at 20 degrees Celsius, see you have a pressure of around 17.54. So that would be around here somewhere. I don't know. If you're at 40, right, you can see it's a little higher. Oh, good grief. Anyhow, you see it's 55.32, whatever. So if you conduct an experiment at 20 degrees Celsius, when you collect that gas, you're going to have to subtract the pressure of the water vapor that's pushing up. Give me a thumbs up if you follow me just on the concept of what the heck is going on in this. You know, it's not even, I guess it is an experiment in a way, but it's just a collection of the gas. Give me a thumbs up if you follow me on just how they collect the gas and the fact that the water exerts some pressure as well. Okay, wonderful. Well, with all that in mind, let's look at a problem where you would be expected to apply what we just looked at. Okay, let me see how much space I gave. Okay, I gave myself a little extra space. Always need some room to run around, right? The student prepares a sample of H2 gas, hydrogen gas, by electrolyzing water. So electrolyzing water just means you pass a current through the water, and that causes it to decompose because it's a non-spontaneous reaction. Anyhow, you electrolyze the water at 20 degrees Celsius. You collect 152 milliliters of hydrogen at a total pressure of 758 millimeters of mercury. After using the table from the previous slide to find the vapor pressure of water, calculate the partial pressure of the hydrogen and the number of moles of hydrogen collected. I think we could even solve this multi-rule here. But anyhow, from Dalton's law of partial pressures, we know that the total pressure of all the gases is going to be equal to the pressure of the hydrogen gas plus the pressure of the water vapor. Now, maybe I should put gas in here just so my students aren't confused that we're talking about water in the liquid phase. So that would mean if I want to determine the partial pressure of the hydrogen, I'm going to take the total pressure and then I'm going to subtract the pressure of the water vapor. Now, the reaction is done at 20 degrees Celsius. Let us back up. And we see that at 20 degrees Celsius, at T is equal to, maybe I'll do it like this. I'll say T of 20 degrees Celsius at T equal to 20 degrees Celsius, the pressure of my H2O is going to be equal to 17.54 millimeters of mercury. Copy that? Let's see here, Dion. Copy. There we go. Good boy. Okay, I'm going to take that back here. Paste it in. Go. Oh, Siri, you're not paying attention. Let's see here. What else? So now we can plug some numbers in. The partial pressure of our hydrogen, let me choose a pencil here, is going to be equal to total pressure, which was 758 millimeters of mercury. Subtract the pressure of water, 17.54 millimeters of mercury. And we find out the pressure is equal to 740.46. I don't know, that's not really the correct way to do it. Let's see here, 758, subtract 17, subtract 17.5. Put 740, the decimal. Millimeters of mercury, like that. So that is equal to pressure, or the partial pressure of our hydrogen. Okay, now we want to figure out the number of moles of hydrogen collected. Maybe I should do the old copy paste trick again. Take this, copy, bring that over here, paste. So we get this from the first part. And to solve for the number of moles of hydrogen collected, we know that PV is equal to nRT. If we want to solve for the number of moles of hydrogen, we have PV divided by RT. We have the pressure of our hydrogen. We're going to need to convert that into atmospheres. And so we can do that right here, 740 millimeters of mercury divided by 760 millimeters of mercury per atmosphere. Do that right up here. The volume is 152 milliliters, so volume is equal to 0.152 liters. I did that one in my head, 152 liters, divided by the gas constant, 0.0821 liter atmosphere per mole Kelvin, multiplied by the temperature, which is what, 20 degrees Celsius. So can we add that to 273? So that means my temperature is equal to 293 Kelvin. 293 Kelvin. Double check the units, millimeters of mercury, atmospheres cancel, liters cancel, Kelvin cancel, and I'm left over with the number of moles of hydrogen that are produced. And when I plug that in, I get my number of moles of H2 is equal to 6.16 times 10 to the negative 3 moles of hydrogen gas, like that. And so there is my final answer. All right, hot dog, we have a wiener. We did it. Give me a thumbs up to follow me on that one. Beautiful problem. All right, great. Well, chemistry is content driven, right? Let's move on to the next subject, which deals with partial pressure and mole fraction. Now, we can rearrange the ideal gas law for a mixture containing two gases, A and B. And we can say that the pressure of A over the total pressure, so that's the pressure, and P total means the pressure of A plus the pressure of B. Okay, maybe I should write that down here. Okay, so P total, where's my pen? P total would be equal to the pressure of A plus the pressure of B. Is equal to the number of moles of A divided by the total number of moles. So N total is equal to the number of moles of A plus the number of moles of B, like that. Okay, well, the mole fraction, X of a gas A, is the number of moles of A. divided by the number of moles of gas in the mixture. And so NA over N total is equal to mole fraction. So we could write that in here is equal to mole fraction. With those two formula in mind, let's see if we can look at that in terms of Dalton's law. Well, if we know that what I have written here, we get a different color pen, okay? If I know that this is equal to mole fraction, I can rearrange that to say that PA, or the partial pressure of A, is equal to the mole fraction of A times the total pressure. And that's the equation that's on the next slide. This one right here, Dalton's law of mole fraction. The partial pressure of gas A is equal to its mole fraction times the total pressure. X is the mole fraction of any individual gas component in a mixture. Again, the mole fraction of A, XA, is equal to the number of moles of A divided by the total number of moles in my mixture. Well, with these equations in mind, let's see if we can use them or apply them to a problem. This is sample problem 5.6. When 1 mole of methane, CH4, is heated with 4 moles of oxygen, the following reaction occurs. We have methane plus oxygen, or 1 mole of methane plus 2 moles of oxygen gives us carbon dioxide plus water. What are the mole fractions of oxygen, carbon dioxide, and water in the resulting mixture? If the total pressure of the mixture is 1.26 atmospheres, what are the partial pressures? Well, let's see if we can figure out the mole fractions of our oxygen, carbon dioxide, and water. All right, what it's asking for is mole fraction of O2, mole fraction of CO2, and the mole fraction of water. Well, remember that mole fraction of A is equal to the number of moles of A divided by the total number of moles. So that means that we have to be able to determine, or we have to determine the number of moles of carbon dioxide, water, oxygen that remain after the reaction. How are we going to do that? Let's see. We're going to start out by rewriting